Hello, and welcome to this second presentation related to the concepts of mass, weight, mass density, and also relative density is now being considered. The work we will review is underpinned by the previous presentation related to mass, weight, and density, as we will be referring to that previous knowledge to analyse slightly more complicated problems. Let's briefly recap some definitions. Definition of mass, which is a scalar property. So mass is defined as the quantity of matter. If we move an object, even taking it to the moon, it does not change the quantity of matter. So the mass is constant. Mass is a scalar quantity, so it has a magnitude but no direction. In the SI system, mass has the unit of the kilogram. Masses can be expressed in tons or in megagrams. And it's worth remembering that 1 ton is 1,000 kilograms and 1 megagram is 1,000 kilograms. Let's consider the calculation of weight force, and weight is a vector property. Everything near the Earth experiences a pulling force towards the Earth. This pulling effect is due to the acceleration of gravity, symbol lowercase g, and internationally taken as being equal to 9.81 meters per second squared on Earth. The effect of gravity acting on an object produces a force on the object, and this force is known as a weight force or simply a weight. In the SI system, weight of an object is expressed in terms of the Newton, symbol capital N. And weight is calculated from Newton's second law of motion. So weight in newtons is equal to the mass in kilograms multiplied by the gravitational acceleration in meters per second squared. So in symbol form, weight W is equal to mass m multiplied by gravitational acceleration g. And as stated previously, the international value for g around the world is 9.81 meters per second squared. Note that weight force is a specific type of force in that it always acts vertically downwards. The weight of an object does change between Earth and, say, the moon. So, for example, a 736 Newton person on Earth would only weigh approximately 123 newtons on the moon. And that's because the gravitational acceleration on the moon is 1/6 of that on Earth. Example 1. Let's calculate the weight of an object on Earth that has a mass of 102 kilograms. So in the question we're given that the mass, m, is 102 kilograms. We always assume that gravitational acceleration, lowercase g, is 9.81 meters per second squared. So to calculate the weight force, W, is simply mass times gravitational acceleration, Newton's second law. So W in this case is 102 kilograms multiplied by 9.81. So that works out to be approximately 1 kilonewton. Here are a few tutorial exercises for you to undertake, very similar to that of the example. Exercise 1, we have to calculate the weight on Earth of an object having a mass of 52 kilograms. Exercise 2, we've got to determine the weight on Earth of a mass of 750 grams. And exercise 3, a lunar rover has a mass of 0.21 ton. We've got to calculate its weight on Earth before liftoff and its weight when landed on the moon. We're told to assume that the moon's gravitational acceleration is 1.635 meters per second squared. The answers to the various questions are shown in the brackets on the right hand side. I would encourage you to stop the presentation and attempt these exercises. The full solutions are shown on the following slides. Exercise 1 is very similar to example 1, so I'll let you review the solution at your own pace. Exercise 2 solution, very similar to example 1 again. Just be careful that the mass is given as 750 grams, so the first thing we must do is to convert the mass into kilograms, kilograms being the base unit in the SI system. But again, I'll let you review that solution at your own pace. Exercise 3 is our lunar rover. Initially had a mass of 0.21 tons. We've got to calculate its weight on Earth before liftoff, and then the weight when it's landed on the moon. And we're told that the moon's gravitational acceleration is 1.635 meters per second squared. So extracting information from the question, the mass M is 0.21 tons. Don't forget there's 1,000 kilograms in 1 ton, so multiplying 0.21 tons by 1,000, we have 210 kilograms as our mass. The Earth's gravitational acceleration is 9.81 meters per second squared. We always assume that unless told otherwise. And the moon's gravitational acceleration given in the question is 1.635 meters per second squared. So calculating the weight on Earth, W here, simply the mass multiplied by the Earth's gravitational acceleration, so 210 multiplied by 9.81 is 2,060 newtons, and calculating the weight on the moon, shown here, that's the same mass but multiplied by the moon's gravitational acceleration, so this time it's 210 multiplied by 1.635, so 343.4 newtons weight on the moon. Tutorial exercises continued. Is exercise 4 here. A machine component has a weight of 3.5 newtons. We've got to determine its mass, so there's a bit of transposition required there. And exercise 5, from an experiment performed on the planet Mars, a known mass of 250 grams weighed 0.93025 newtons on the Martian surface. We're asked to determine the gravitational acceleration on Mars. Again, the answers are shown in the brackets on the right hand side. I would encourage you to start the presentation and attempt these exercises, but the full work solutions are shown on the following slides. Exercise 4, solution. The machine component has a weight of 3.5 newtons. We've got to determine the mass. So given the question weight W, 3.5 newtons, we assume the gravitational acceleration on Earth to be 9.81 meters per second squared. From the equation, weight force is equal to mass times gravitational acceleration. So in this question we have to rearrange to find the mass. So dividing both sides by G, the mass is equal to W divided by G. The W, the weight, is 3.5 newtons. The G, the gravitational acceleration, is 9.81 meters per second squared. That evaluates to 0.35 kilograms, or in terms of grams, that's 357 grams, as stated in the question. Always remember that the base unit in the SI system is the kilogram. So exercise 5, from an experiment performed on planet Mars, a known mass of 250 grams weighed 0.93025 newtons on the Martian surface. We've got to determine the gravitational acceleration on Mars. So from the question, we know the mass is 250 grams. Again, converting that to kilograms, that's 0.25 kilograms. The weight on the Martian surface is 0.93025 newtons. We know that the weight on Mars is equal to the mass multiplied by the gravitational acceleration on Mars. So rearranging for the gravitational acceleration G, that would be the weight divided by the mass. So inserting the values from above for weight and for mass, the gravitational acceleration on Mars is 3.721 meters per second squared. Let's recap mass density, usually given the symbol ρ. That's a Greek symbol, looks like a italic P. So if the mass of an object is unknown, it can usually be found quite easily from the density. Density is a measure of the quantity of matter in each unit of volume. So mass density, symbol ρ, is defined as mass divided by volume. So ρ is equal to m divided by v. Mass density has the derived SI unit of the kilogram per meter cubed. And remember, the kilogram per meter cubed can be written as kilogram meters to the -3 using the negative index. Relative density, usually given the symbol lowercase sigma. It's like a sideways 6. The relative density of a particular substance is the ratio of its density to that of water at 4 degrees C in atmospheric pressure, which has a density of 1000 kilograms per meter cubed. So in other words, relative density, sigma, is the density of the substance you're considering divided by the density of water, which is 1000 kilograms per meter cubed. The mass density of mercury is 13,600 kilograms per meter cubed. We've got to calculate its relative density. So relative density, as shown above, is the density of the substance divided by the density of water. So the mass density of mercury is 13,600 kilograms per meter cubed. The mass density of water is 1000 kilograms per meter cubed. So that evaluates to a ratio of 13.6. Notice that relative density is dimensionless because it is basically a ratio of two mass densities. And purely for reference, the relative density, sigma of 13.6, is the same as the mass density, symbol ρ, in terms of grams per centimeter cubed. So 13.6 grams per centimeter cubed is the same as the relative density. Although non-preferred units, you do sometimes see densities quoted in terms of grams per centimeter cubed. That's just for reference. Also notice the density of water stated here relates to fresh water. Seawater has a higher density because of the salt content. There's an exercise for you to undertake. If oil has a density of 800 kilograms per meter cubed, we've got to calculate its relative density. And if the relative density of aluminium is 2.7, we've got to calculate its mass density. I would encourage you to start the presentation and attempt that exercise, but the answers are shown on the following slide. The answers to the exercise are given in the question that the oil has a mass density of 800 kilograms per meter cubed, so that's the mass density symbol ρ. So to find its relative density relative to water, we divide the 800 by 1000 kilograms per meter cubed, the fresh water density. That gives a relative density of 0.8. In the second part of the question, we're given a relative density of aluminium. It's 2.7, so that's the relative density, symbol sigma. To find the mass density, we multiply the relative density by the density of fresh water at 1000 kilograms per meter cubed. So the actual mass density is 2,700 kilograms per meter cubed. So again, notice that relative density has no unit and mass density has the unit kilograms per meter cubed. Mass density, alternative units. One of the issues students sometimes have is the wide array of units that can be used. So the information on this slide is just for reference, outlining the other units that are sometimes quoted in various reference sources. So densities can be stated in terms of ton per meter cubed, kilogram per litre, grams per milliliter. And what I've done here is try to show you some various conversions here. One thing to remember is that 1 litre is the same as 0.001 meters cubed, or 1000 litres is equal to 1 meter cubed. Note that 1 megagram per meter cubed is the same as 1 ton per meter cubed, is the same as 1 kilogram per litre, it's the same as 1 kilogram per decimeter. 1 kilogram per meter cubed is the same as 1 gram per litre, same as 1 gram per decimeter cubed, same as 0.001 gram per centimeter cubed. And again, the mass density of water is very important to remember. So density of fresh water, rho, is 1000 kilograms per meter cubed, or that could be written as 1 megagram per meter cubed, or that could be written as 1 ton per meter cubed, or 1 kilogram per litre. Each of those relates to the same density but in different units. Don't be too concerned with the information on that slide. It looks very confusing. We will not refer to this wide array of units within this presentation, but within vocational practice you may well encounter some of the other mass density units, so be aware of them. Example 2. Given that the mass density of aluminium alloy is 2,700 kilograms per meter cubed, we've got to determine the weight of a piece of round bar having an outside diameter of 57 millimeters and a length of 1.2 meters. If the bar was now made of stainless steel having a relative density of 8.2, what now is the weight of the bar? So 2 parts to the question, call them A and B. So here's our solution. So in the question we're given the mass density of the aluminium alloy is 2,700 kilograms per meter cubed. We're given the outside diameter of the bar, 57 millimeters. Notice that's been converted straight away into meters, divided by 1,000. And the length of the bar also given in the question, 1.2 meters. Part A of the question, which is the bar made from aluminium alloy. First thing we're going to do is calculate the area and then the volume. So the cross-sectional area of the bar A is pi d squared upon 4. We're given in the question the diameter in terms of meters here. So that evaluates to a cross-sectional area of 2.552 times 10 to the negative 3 meters squared. And then to calculate the volume of the bar, this is a prismatic section, so constant section. So the volume is simply the cross-section area multiplied by the length. So the volume is the area calculated above multiplied by the length of 1.2 meters. So our volume is 3.0621 times 10 to the negative 3 meters cubed. Example 2 continued. Just repeated the volume calculation for convenience. So the next thing we need to do is to calculate the mass of the bar. So we'll be using the density equation, rho is equal to m divided by v, and transposing for m, so multiplying both sides by v in this case. The mass of the bar is the density multiplied by the volume. The density is given in the question as 2,700 kilograms per meter cubed for the aluminium alloy, and the volume is stated above. So evaluating the mass of the aluminium alloy bar is 8.268 kilograms. Calculate the weight of the aluminium alloy bar. Weight is equal to the mass times the gravitational acceleration. So the mass calculated above multiplied by 9.81 meters per second squared. We have a weight of the aluminium alloy bar as 81.1 newtons. Now for part B of the question, we have to consider the same bar, but this time made from stainless steel, not aluminium alloy. We're given in the question the relative density, sigma, of the stainless steel, it's 8.2. So to calculate the mass density of stainless steel, we simply multiply the 8.2 relative density by the mass density of water, 1,000 kilograms per meter cubed. So the mass density of stainless steel is 8,200 kilograms per meter cubed. Now to work out the weight of the stainless steel bar, we can simply ratio the weight of the aluminium alloy bar with the ratio of densities of stainless steel to aluminium alloy. In other words, this simplifies the above calculations. So in this case, the weight of the stainless steel bar is the weight of the aluminium alloy bar multiplied by the mass density of stainless steel, 8,200, divided by the mass density of aluminium alloy, 2,700. That evaluates to 246.3 newtons. So for the same volume of bar, the stainless steel is around 3 times heavier than the aluminium alloy bar. So obviously the choice of material, the density of material, affects the weight of the bar. Exercise 2, this is for you to attempt. You have to calculate the weight of 200 titanium washers having an outside diameter of 20 millimeters, shown in the sketch here, and an inside diameter of 6.4 millimeters, shown here. The thickness of the washer is 1.5 millimeters. In the question, we're given the relative density of titanium is 4.59, and also a hint in the question to use the formula for the area of an annulus for calculating the area of the washer. So area of the annulus is equal to pi multiplied by, in brackets, the outside diameter squared minus the inside diameter squared, or divided by 4. I would encourage you to start the presentation and attempt this question. The answer is shown in the bracket here, but the full work solution will be shown on the following slide. Exercise 2D, here's the solution. We've got to calculate the weight of 200 titanium washers. So, extracting information from the question, the first thing to deal with is the relative density. So, sigma is 4.59. We need to calculate the mass density, rho. So that will be 4.59 times the density of fresh water, 1,000 kilograms per meter cubed. So our mass density of titanium is 4,590 kilograms per meter cubed. The question states the number of washers. There's 200 of them. We've got the outside diameter, D, so 20 millimeters stated in the question, but I'm converting that to meters because our density is in terms of meters. So 20 millimeters is 0.02 meters. The inside diameter, little d, 6.4 millimeters, so that's 0.0064 meters. And the washer's thickness is 1.5 millimeters, so that's 0.0015 meters. Exercise 2 continued. So first of all, let's calculate the area of one washer. So given the formula in the question, we can insert the outside diameter, inside diameter, and evaluate the area, and that's 0.282 times 10 to the negative 3 meters squared. Next, we need to calculate the volume of one washer. So V is equal to the cross-section area multiplied by the thickness of the washer. So the volume is equal to the area, calculated above, multiplied by the thickness, again stated above. So the volume is 0.423 times 10 to the negative 6 meters cubed. We can now calculate the mass of one washer. Mass is the density multiplied by the volume. So mass is the 4,590 kilograms per meter cubed density multiplied by the volume, calculated above. So the mass of one washer is 0.00194 kilograms. If we want to calculate the weight of one washer, lowercase w here, that will be mass times gravitational acceleration. So the mass calculated above, multiplied by 9.81 meters per second squared. So the weight of one washer is 0.019 newtons. And the question states we have 200 washers, so the total weight is the 0.019 above multiplied by 200. So 3.81 newtons is the total weight force of the 200 titanium washers. Let's now consider some tutorial questions. Here's question 1. A circular aluminium alloy bar with a diameter of 50 millimeters, lengths of 200 millimeters, has a mass of 1.1 kilograms. We've got to calculate A, the density of the alloy, in kilograms per metre cubed, and B, the relative density of the alloy. Question 2. If copper has a density of 8,890 kilograms per metre cubed, we've got to calculate the mass in kilograms of a copper bus bar of rectangular section 50 millimeters by 60 millimeters by a length of 7.5 meters. The answers are shown in the brackets on the right hand side. I would encourage you to stop the presentation and attempt these questions, but the full solutions are shown on the following slides. Here's question 1 solution. I'm just going to very briefly talk you through the solutions. We're given in the question the diameter of the bar. It's 50 millimeters. As always, I'll convert that straight into meters. It's 0.05 meters. And we're given the length of the bar, 200 millimeters again, in meters, 0.2 meters. In this particular question, we're given the mass of the bar, it's 1.1 kilograms. We've got to calculate A, the density of the alloy, given the above information, and part B, the relative density of the alloy. So for part A, first thing I've calculated is the volume. I know the volume of a cylinder is pi d squared upon 4 multiplied by L, so that's what's shown there. We've got the diameter above in meters, we've got the length in meters. We can evaluate the volume in meters cubed, and to calculate the density, that's rho is equal to mass divided by volume. We're given the mass in the question, we just calculated the volume above, so we can find the mass density of the aluminium alloy. It's 2,801 kilograms per metre cubed. Part B, to find the relative density, we just simply divide the mass density by density of water. So relative density is the density of the aluminium alloy divided by the density of water. So 2,801 divided by the 1,000 kilograms per metre cubed for fresh water. So the relative density is 2.8. Question 2 solution. In this case, we're given copper having a mass density of 8,890 kilograms per metre cubed. We're given the dimensions of the buzz bar. We're given the geometry of the buzz bar. We know what the width is, stated in millimeters, but I've converted that to meters. We know what the depth or the thickness is, again stated in millimeters, converted to meters. And we're given the length of the buzz bar, that's in meters. In the question, we're asked to calculate the mass in kilograms of this copper bus bar. So the first thing I need to do is calculate the volume. So volume will be the breadth times the depth times the length of the bus bar. So inserting the above dimensions, the volume of the bar is 0.006 meters cubed. In step 2, knowing that density rho is equal to m divided by v, we can rearrange the equation for the mass m. That's the rho multiplied by the v. So inserting the values above, we find that the mass of the bus bar is 53.34 kilograms. Tutorial questions continued. Here's question 3. Assuming the relative density of steel to be 7.84, we've got to calculate the weight per meter run of A, circular bar having a diameter of 50 millimeters, B, a flat bar of section 50 millimeters by 60 millimeters, and C, a pipe of outside diameter 8 centimeters and wall thickness 1 centimeter. We're given a hint in the question to calculate the mass per meter, shown as m dash here. It's simply going to be the density multiplied by the cross-sectional area. Question 4. Assuming the mass density of steel to be 7,839 kilograms per meter cubed, we've got to calculate the weight of 1,000 steel washers of outside diameter 40 millimeters, inside diameter 20 millimeters, and the thickness of 3.2 millimeters. As always, the answer is stated in the brackets. I'd encourage you to start the presentation and attempt these questions. The full solutions are shown on the following slides. Question 3 solution. 3 parts of the question here. Let's first of all extract the information from the question. We're given the relative density of steel to be 7.84. So my sigma for steel is 7.84. So don't forget, solids and liquids are always relative to water. So the mass density symbol rho is going to be 7.84 multiplied by 1,000, so 7,840 kilograms per meter cubed. Now we know that mass, m, is equal to the density multiplied by the volume. But these are all prismatic sections here. In other words, they're constant sections. So the mass could be written as the density multiplied by the area times the length. The area times the length is how we work out the volume of a prismatic section. We're actually asked to calculate the mass per meter in the question. So if we divide both sides of this equation here by L, then the mass per unit length is equal to the density multiplied by the cross-sectional area. So what's happened on the next line, I just denoted the m divided by L as m dash, just for convenience. So m dash is equal to the density of the material multiplied by cross-sectional area, and that will give me the mass per meter. Within material suppliers information, you often see data stated as mass per meter for ease of reference. And once we've got the mass per meter, we can then calculate the weight per meter simply by multiplying by 9.81 meters per second squared. So question 3 continued. This is part A. We're considering the circular bar of diameter 50 millimeters. So the first thing I would do is work out the area using my formula pi d squared upon 4. Inserting the diameter given in the question, I can work out my cross-sectional area for the bar. To find the mass per meter, it's simply the density times the area. So the mass per meter is the 7840 kilograms per meter cubed. That's the density of the steel. And I multiply by the area calculated above. That gives me the mass per meter in kilograms per meter. And to calculate the weight per meter, that's simply the mass per meter times the gravitational acceleration. So the mass per meter from above multiplied by 9.81 meters per second squared. So the weight per unit length is 151 newtons per meter. Question 3, part B. This is the flat bar now, 50 millimeters by 60 millimeters. Obviously those dimensions are converted into meters. But the same process involved here. Calculate the area, calculate the mass per meter, and then calculate the weight per meter. I'll let you work through these calculations at your own pace. And question 3 continued again, part C. This time we have a pipe with an outside diameter 8 centimeters and a wall thickness of 1 centimeter. So be careful with the information given here. The first thing to do is to convert the centimeters into meters, and also the wall thickness from centimeters to meters. So to calculate the area using our standard formula for a pipe or an annulus, we need to know both the outside and the inside diameter. So we need to calculate the inside diameter. Be careful when you calculate the inside diameter, it's the outside diameter minus twice the wall thickness, so be careful there. So the outside diameter is 0.08 meters, and then the wall thickness is 0.01 meters, but of course there are 2 wall thicknesses to take from the outside diameter to calculate the inside diameter. So the inside diameter is 0.06 meters. That's usually where students make a mistake. They forget to multiply the thickness by 2 or when they're calculating the inside diameter. Once we know the outside diameter and the inside diameter, we can calculate the area. And as before, we can then calculate the mass per meter and calculate the weight per meter. Again, I'll let you work through the calculation at your own pace. Here's a solution for question 4. I'll let you work through a solution at your own pace as it's very similar to exercise 2D we reviewed previously. And question 4, solution continued. Again, I'll let you work through the solution at your own pace. Some more tutorial questions. Question 5. Assuming the density of steel is 7,840 kilograms per meter cubed. We've got to calculate the length of the steel pipe of outside diameter 4 centimeters and wall thickness 3 millimeters that can be expected from 1 ton of the piping. So though that seems a more unusual question to the ones we've considered previously, we will still go through the same process of finding the area, finding the volume because you're given the mass in this particular case, and then from that you can rearrange the appropriate equations to find the length. I'll let you think through question 5. And question 6, a rivet can be considered to be a hemisphere, that's half a sphere, of radius 20 millimeters, together with a cylinder of diameter 25 millimeters and length 70 millimeters. The rivet's material density is 7.84 tons per meter cubed. Be careful with the density given. We've got to calculate the mass of 100 rivets. In the question, we're informed that the volume of a sphere can be calculated from the equation 4 pi r cubed divided by 3, where r is the radius of the sphere. Again, a fairly thought-provoking little question, but we'll undertake the same kind of procedure as in previous questions. So working out the volume of the rivet, but of course in this case it's broken into 2 sections, the hemisphere and the cylindrical shank. But from that we can find the total volume, and then the procedure is very similar then to find the mass of 100 rivets. Again, the answers are shown in the brackets on the right hand side. I would encourage you to stop the presentation and attempt question 5 and 6 now, but I'll show you the full solutions on the following slides. Question 5, solution. So we're given in the question the mass density of the steel. We're given the outside diameter of the pipe. Again, convert the dimensions to meters because the mass density is in terms of meters cubed here. Wall thickness is stated, so from that we can find the inside diameter of the pipe. This particular question has stated the total mass of the piping, M, it's 1 ton. Don't forget, a ton is 1,000 kilograms. So we can work out the area of the pipe section from our standard formula here, inserting the above dimensions to calculate the area in terms of meters squared. Question 5, solution continued here. So part 2, from density is equal to mass divided by volume. We can rearrange to find the volume, it's mass divided by the density. We're given the mass in the question, it's 1 metric ton. It's 1,000 kilograms, and we're given the mass density in the question, 7,840 kilograms per meter cubed, so we can calculate the volume in meters cubed. Now, the volume is equal to the area multiplied by the length, again for a prismatic section, which the pipe is, a constant section. We can simply rearrange to find the length, so the volume divided by the area calculates the length. So this is the length of the pipe that should be expected from a mass of 1 metric ton. This is question 5 solution continued, just an alternative version of calculating the length of the pipe. It's a slightly condensed solution and avoids actually calculating the volume of the pipe. I'll let you review it at your own pace for your interest. Question 6, solution. In the question we're given the rivet head radius, again converting the dimensions to meters. We're given the rivet shank diameter, converted to meters here, and we're given the rivet shank length, again converted to meters here. Notice that the mass density given is 7.84 tons per meter cubed, but remember a metric ton is 1,000 kilograms. So we can write that as 7,840 kilograms per meter cubed. Question 6, solution continued. So calculating the volume of the rivet is slightly more complicated than previous questions because we have 2 parts to calculate. So the first thing we need to do is calculate the volume of the head of the rivet. And notice that the head of the rivet is effectively a hemisphere. But in the question, we are given the volume of a sphere. But when I calculate the volume of the head, I use the formula for volume of a sphere, 4 pi r cubed upon 3, shown here. But I've factored it by a half because we have a hemisphere, which of course is half a sphere. So be very careful when you're working out the head of the rivet. The formula given is for a sphere, like a football shape, but we have half of that. So you need to account for that when you calculate the volume of the head. But from the equation, I can calculate the volume of that head in meters cubed. Then to calculate the volume of the shank, this is the shank of the rivet, shank volume is simply the volume of a cylinder. So I can work out the volume of the shank. To find the total volume, I simply add up the head and the shank volumes. So the head volume calculated above, added to the shank volume again calculated above. So the total volume of the rivet. We can calculate the mass of the rivet M from the density multiplied by the volume. We're effectively given the mass density in the question. Just calculated the volume of the rivet. So we can calculate the mass of one rivet, and then to find the mass of 100 rivets, we simply multiply the mass of one rivet by 100. So approximately 40.1 kilograms is the mass of the 100 rivets. Tutorial questions continued. This is question 7. A hollow float, shown in the sketch, is closed at both ends and has an external appearance of a cylinder. The outside dimensions are a diameter of 20 centimeters, so across here that would be 20 centimeters. A depth of the float is 10 centimeters, so this is 10 centimeters. And there is a constant wall thickness of the float of 5 millimeters. The wall thickness of the side of the float and the top and bottom of the float is constant. We've got to calculate the float's mass and weight, assuming that the mass density is 8.4 times 10 to the 3 kilograms per meter cubed. The answers are shown here. I would encourage you to start the presentation and attempt this question, but I will show the full worked solution on the following slide for your reference. So question 7, here's the solution. I'm actually going to let you review this solution at your own pace with no input from me. So here's the first slide to the solution. One thing to note is that the constant wall thickness of the float. So this thickness here, top and bottom, is the same as the wall thickness stated here, 0.005 meters. Question 7, solution continued. Evaluating geometry here. Question 7, solution continued. Evaluating the volume, the mass and the weight of the float. Calculate the volume of the float. It's essentially the outside cylinder minus the inside cylinder. Tutorial questions continued. Question 8. We're asked to find the weight to the nearest Newton of a non-right angled triangular gusset plate, as shown in the sketch here, which has side lengths of, and be careful how you read the information, A, shown here, of 269 millimeters, B, shown here, of 200 millimeters, and side C, shown here, of 180 millimeters. The thickness of the plate is 60 millimeters, and the mass density of the material is 7.84 tons per meter cubed. There's a note in the question: to calculate the area of the triangle, we can use the S rule, which is shown here. So the area of a triangle A is given by the formula shown here. where S is the semi-perimeter, and that's calculated from a half of, in bracket, side A added to side B added to side C. The weight of the gusset plate is shown here in the bracket. I'd encourage you to stop the presentation and attempt this question, but the full work solution is shown on the following slides. So question 8, here's the solution. I'm going to let you review it at your own pace. Just be careful extracting information from the question for the mass density, and also be careful when you apply the S rule formula, you use the appropriate values in the question. This is the area of the triangle. Question 8, solution continued here. Just repeated the S rule calculations from the previous slide for convenience. We can now calculate the volume, the mass and the weight. The question says to calculate the weight to the nearest Newton, so that would be 22 Newtons in this particular case. Finally, I will leave you with a couple of questions to attempt on your own. This is question 9. I'll let you read the question at your own pace. The answers are shown at the bottom here. And also question 10. Again, I'll let you review this at your own pace. Answers are shown in the bracket. Here's a bibliography used to help generate this presentation. And I hope it's been of interest to you. And thank you for viewing.